Good morning, everyone. My name is Jung Sini. Today, I want to share how I brought computational thinking into a year-4 science lesson on photosynthesis through two connected projects called the Brain Total Mission. Project 1 is unplugged activity using investigation cards, and Project 2 is plugging activity using a scratch game I built myself. Let me quickly outline what I will cover. First, I will explain the real-world problem that started this whole mission. Then I will show how Project 1 and Project 2 connect to each other. After that, I will walk through the 5 computational thinking skills in action across both projects. Following this, I will discuss the benefits of this integration for both teachers and students. Finally, I will close with a short conclusion that ties everything together. Every good science investigation starts with a real problem, and this one is no different. In my story, the school gardener noticed that several plants in the garden are unhealthy. The leaves have turned yellow, the plants are growing slowly, and some of them are producing fewer flowers. This raises a simple but important science questions. Why can't these plants make enough food through photosynthesis? I choose this problem because it is something students can actually observe in real life, whether in a school garden, a home garden, or a nearby farm. This makes the learning feel relevant rather than abstract. Let me now introduce Project 1, which is the unplugged activity. By the end of this activity, students should be able to state the requirements of photosynthesis, identify its products, solve a simple and broad problem, explain why photosynthesis matters, and apply all 5 computational thinking skills. To achieve these objectives, students take on the role of plan tutors. They work with plan investigation cards, worksheets, tables, flowcharts, and group discussion, all without touching a computer. So, how does Project 1 actually work in the classroom? Students work in small groups and receive a set of plan investigation cards. From there, they observe the condition of each plan, identify what requirement is missing, and complete a worksheet based on their findings. Then, they write simple if-then rules, complete a decision flow chart, and finally, share their answer with the class. Because this activity is hands-on and simple to follow, it is suitable for year 4 students very well. Once students has built this foundation, they can move on to project 2, the plugin activity. By the end of this activity, students should be able to apply their photosynthesis knowledge inside a scratch game. Use computational thinking through coding logic, receive immediate feedback on their answers, strengthen their problem solving skills, and enjoy an interactive learning experience. To meet these objectives, students play the Plain Total Mission Scratch game, which includes a start page, a mission page, 4 plan levels, instructions, and a feedback and result system. In terms of how it actually plays out, students use the very same science knowledge from Project 1. But now they apply it inside a digital environment. The game is story driven and interactive from start to finish. Students read the mission, check each plan using the investigation buttons, choose what they believe is the correct answer, receive feedback right away, and then move on to the next level. Through this process, students get to practice computational thinking in a format that feels more engaging than a worksheet. With that connection in mind, let us look at the 5 computational thinking skills that run through both projects. These are decomposition, which means breaking a big problem into smaller parts; pattern recognition, which means finding similarities and repeated relationships; abstraction means focusing only on the important information; algorithms, which means using step-by-step instructions to solve a problem; and the last, evaluations, means checking whether a solution is correct. In the next few slides, I will show exactly how each of these skills appears in both Project 1 and Project 2. Let us begin with decomposition. In Project 1, students break the investigation down by checking 4 separate requirements, namely sunlight, water, carbon dioxide, and chlorophyll. In Project 2, the game mirrors this exact structure by giving students separate patterns to investigate each requirement individually. Moving on to pattern recognition, which means finding similarities and repeated relationships. In Project 1, students compare playing cards A to D side by side. In Project 2, every label follows the same pattern of observe, diagnose, and solve. Once students recognize this repeating pattern, they can predict what to do next in any level without needing new instruction each time. Next comes abstraction. In Project 1, students sort the information into 2 groups. The important information is sunlight, water, carbon dioxide, and chlorophyll, while the unimportant information includes details like pot color and plant name. In Project 2, this same thinking shows up in the code itself, where one single game structure is reused for all planes rather than being rebuilt from scratch in each time. Turning to algorithms, in Project 1, students create simple if-then rules to guide their reasoning. In Project 2, the Scratch game uses if and else coding blocks to carry out the same logic automatically. Together, these examples show students how scientific reasoning can be turned into a clear, repeated procedure. The final skill is evaluation. In Project 1, students evaluate their thinking by comparing their predictions with what they actually observed on the playing cards. In Project 2, the game evaluates the student automatically, responding with correct, incorrect, or try again. In both cases, students are learning the same underlying habit, which is to check their own thinking and improve it when it turns out to be wrong. To bring all 5 skills together, this table places Project 1 and Project 2 side by side. Decomposition appears as investigating plain requirements on one side and separate investigation buttons on the other. Pattern recognition appears as comparing plain cards matched with a repeated game structure. Abstraction appears as focusing on important information matched with a reusable game design. Algorithms appears as if-then rules matched with if-else coding block. And Evaluation appears as checking answers matched with automatic feedback in the game. Seeing it laid out this way makes it very clear that both projects are teaching the same underlying thinking, just through two different tools. Now, let us turn to why this integration actually matters. Starting with the benefits for students. This approach helps students build understanding gradually, moving from concrete materials to digital application. It makes science content easier to remember, strengthens logical thinking and problem solving, and encourage teamwork through discussion. In addition, the Scratch game gives students immediate feedback, and the interactive format makes learning more fun and engaging overall. Because students think first and apply second, they end up understanding photosynthesis at a deeper level than they would through memorization alone. The integration also brings clear benefits for teachers. It supports different learning styles within a single unit, since some students respond better to hands-on tasks while others respond better to digital gameplay. It makes science lessons feel more creative and active, and it provides clear evidence of student understanding through both worksheets and game results, which in turn makes assessment more straightforward. Furthermore, it allows teachers to connect science content, computational thinking, and digital learning within one coherent lesson, guiding students smoothly from simple reasoning toward digital problem solving. In conclusion, Project 1 and 2 both solve the same real-world problem, which is understanding why the plants in the garden are unhealthy. Both projects successfully integrate the same five computational skills, which is decomposition, pattern recognition, abstraction, algorithms, and evaluation. The unplugged activity develops students' thinking, while the plugging activity strengthens and applies that thinking in a new context. Together, these two projects demonstrate that computational thinking can make science learning more meaningful, more engaging, and more effective. That's all from me. Thank you for your listening.